Hello and welcome! Today we're diving into a question that sounds incredibly simple, but trust me, has a surprisingly complex answer. What does it actually mean for two things to be the same? We're about to explore a fascinating logical world where almost isn't just good enough, it's a core part of the system. Okay, let's just jump right in. Take a close look at your screen. Are these two colors exactly the same? One is hex code FF5733, the other is FF5734. Now, the answer might actually depend on your monitor, your eyes, or maybe even how much sleep you got last night. And that is the central problem here: vagueness.
You see, the problem is that traditional logic is totally binary. It needs a hard yes or a hard no, true or false, identical or different. There's no in-between. But our reality, the world we actually measure and interact with, is completely filled with almost, close enoughs, and these tiny, tiny differences that might matter or they might not. So, to handle this messy reality, we can't just throw our hands up and say it's impossible. We need a new kind of logical tool, one that's built to work in that gray area between absolute perfect identity and obvious difference. So, what if we could build a whole system not on this rigid idea of perfect equality, but on the concept of being indistinguishable within a certain limit? What if we could create a formal, rigorous logic for closeness itself?
And that's exactly what this is all about. The core concept is called indiscernibility. It's a formal way of saying two things are close enough based on a specific threshold, a tolerance, that we choose. Think of it like a margin of error in an experiment. It's a very precise way of defining what good enough for our purposes actually means.
Okay, now I know this slide looks pretty technical, but don't worry about all the terms. All this is here to show you one crucial thing. This isn't some vague, hand-wavy idea. It is a real, rigorous mathematical system. It has solid, predictable rules that logicians have worked out, which allows this idea of closeness to fit neatly into the wider world of logic. So, we have rules for closeness, but what happens if we start chaining them together? You know, if A is close to B and B is close to C, does that guarantee A is close to C? Let's explore that using an operation called composition, and this, my friends, is where things get really, really interesting. Just think of composition as stacking layers of similarity. We start with our basic close enough rule, and then we just apply that rule to itself again and again. What we're trying to figure out is, how does this chain of almosts actually behave? Let's start simple. In something called natural indiscernibility, we basically just decide to ignore the small differences entirely. We're going to treat almost the same as if it's exactly the same. And as you can probably guess, this behaves in a very predictable, straightforward way. But here's the huge twist. On the left, with that natural, simplified composition, stacking a closeness of alpha and beta just gives you alpha plus beta. Simple addition, no surprises. But look at the right. When we use a real metric, a real measurement of difference, alpha, and compose it with itself, we don't get a single crisp number. The uncertainty actually grows. The result becomes an interval, a range of possibilities from alpha all the way to 2 alpha. We've actually lost precision. This is a massive shift in thinking. We've gone from the simple arithmetic of numbers to something called interval arithmetic. Stacking similarities doesn't give you a sharper similarity. It gives you a bigger range of possibilities. Certainty has literally been replaced by an interval. And this seemingly small mathematical detail leads us to a mind-blowing conclusion about the very nature of identity. This isn't just a curiosity, it fundamentally changes how we can model the world. To really get this, let's visualize it. Imagine we apply our rule of indiscernibility just once. We get this result, R1. It's crisp, it's well-defined, we know exactly what's inside the shape and what's outside. Now let's compose it with itself. Apply it a second time. We get R2. And look what happens. That sharp boundary is gone. It has expanded. It's gotten a little fuzzy, a little fatter. Our certainty about the edge has decreased because that interval has grown. And by the third application, R3, the effect is even more obvious. The shape is way more blurred. Every single time we stack another layer of almost, we introduce more and more uncertainty about where the precise boundary actually lies. This perfectly illustrates a fantastic phrase from the source material. This process is, literally, blurring the universum. It's a formal, mathematical model for how certainty and precision can degrade over repeated steps. So here's the crucial point. This is way more than a math trick. It's a powerful way to generalize the concept of identity.
Identity doesn't have to be a razor-thin line. It can have dimension, it can have thickness, it can be a range. So, what do we take away from all this? First, identity can be much more flexible than just same or different. Second, this idea of closeness isn't vague at all. It can be described with a rigorous, formal logic. But the big insight is that stacking real, measured similarity doesn't make things more similar. It creates an interval, a whole range of possibilities. And that gives us an incredible new tool to formally model the inherent vagueness of the world around us.
And that leaves us with a final, provocative thought to chew on. We are so used to thinking of identity as a fixed, absolute point. But what if that's just a special case? What if, in the real world, identity is almost always an interval, a range? What changes when we start seeing the world that way?